Can I get your attention? Good afternoon. Welcome to class. We're going to do routing, and routing today. Okay? At least three very important classes of routing algorithms, two of which operate within a network, and the third, inter-domain routing up there, operates across all of the internet. I left the previous class with an introduction to the classification of routing algorithms. It's safe to say that the routing that's what classification slide again. Attention again, please. Sorry about that. I don't know what just happened. It's safe to say that the routing algorithms, both of the ones that we're going to look at in great detail, and the ones deployed in practice in any non-trivial, meaning reasonably large network, not just like a single router or two-router network, will be dynamic in that you want the routing protocol to automatically or dynamically adapt to the current conditions, possibly failures or changes in the network topology, link weights, and so on, right? But this other distinction, the global versus decentralized, is very important, okay? These are two fundamental classes of algorithms. Decentralized, like I said, does not mean the same thing as distributed. All of these protocols are distributed, okay? There's distributed entities. They are routers, endpoints, and so on, switches across a geographically wide area, right? Wide area networks. They're all distributed. However, the decentralized is just referring to a design aspect. And this was the view I introduced to you between global and decentralized. When we talk about global algorithms, this is the graph of the network. That's it, the graph, the entire network. The global algorithm develops and is a picture of the entire network. So it's as if you have a global view of the network. Whereas a decentralized algorithm, I'm just giving names to these nodes, A, B, C, D, and so on. A decentralized algorithm does not have such a global view and does not try to even maintain such a global view in the process of its operation. Instead, the view it has is local. Okay, that's why it's called decentralized. So the view from A's perspective is going to be as follows. Well, initially it will know only its neighbors, but over time, it will know of the existence of other nodes, of course, because it has to reach all the nodes in the network, but it won't know of any topological aspects beyond its immediate vicinity. Okay? That's the big difference in global and decentralized algorithms. Just by knowing its immediate topology, which is trivial to know, and exchanging messages with its immediate neighbors, A, over time, is going to know how to get to, let's say, node E, whose existence it knows of, but topological path details it doesn't know of. How is this possible? possible? Well, from A's perspective, getting anywhere in that network, these both are referring to the same network. From A's perspective, getting anywhere in this network, there's only two choices it has. Either the destination is itself, in which case there's nothing to do, or it has to go through either B or C. Those are the only two options. So as long as it knows over time, to get to G, do I have to go through B or do I have to go through C? To get to E, do I have to go through E or through C? That's all the information it needs, and it can develop this over time just by talking to B and C, okay, without knowing the topology of the rest of the network. It's very cute, clever, an algorithm, we'll see. It's what's called a distance vector class of algorithms. The linked state class of algorithms, the global algorithms, they're maybe the more intuitive kind. Dijkstra's algorithm you're familiar with, for example, is an example of a global algorithm that just does a shortest path computation on the graph. Okay? So I'm just on that side because I need to point upward. Let's start with the first class, linked state. Linked state algorithms are global algorithms. Distance vector algorithms are decentralized algorithms. Okay? So we'll first look at these in the abstract. What is a linked state algorithm? How does it function? And then we'll look at what are popular real world linked state or distance vector algorithms. Just like we did for TCP, right? Studying reliable transport first in the abstract, and then just said, oh, TCP is just like go back and cumulative acts. It handles reordering, has all the acts and timeouts acts, sequence numbers and so on. Like in the RDP protocols. Similarly, we're going to start conceptually with the linked state routing protocols. So we know that it's a centralized algorithm, which means that it develops the entire, so centralized or globally the same, not decentralized. It develops a global view of the network topology. And all nodes over time have the same picture of the entire network. Okay, how do they develop this picture? Well, they exchange messages with each other. What messages? The messages are telling them what the state of the link is. Is there a link between B and E? If so, what is its state? Is it up? Is it down? What is its weight? And so on. Linked state algorithms disseminate this information or broadcast this information to the entire network, and over time the entire network comes to have the entire graph. All nodes in the network have the entire graph. Each node in the graph is going to compute the shortest or least cost path to all the other nodes in the network. Okay? The algorithm is iterative. It is basically Dijkstra's algorithm. Right? I'm going to introduce some terminology to explain the algorithm. It is an algorithm most of you you've seen, right? In your algorithm 311? Okay. Great. All of you have seen Dijkstra's algorithm, so we just move on. Or let me ask, since every one of you has seen Dijkstra's algorithm, who can tell me what it is in 15 sentences? Yeah? What's your name?
I'm Ben.
Ben. All right, Ben's going to tell us.
It takes a graph, and it takes a node, and it finds all the shortest paths from that node to all other nodes in the graph.
Yes, that I already told you, but how does it work?
Well, it uses a queue of edges. It iterates from that node, all the nodes it can reach. It'll take the shortest one, and it'll add the edges it can reach from there.
It'll add.
Well, first it sets the distance to all infinity, and then it goes through and it relaxes all the edges as it goes.
What's the iterative step? You were saying it'll add what?
It'll check the edges that it can reach, and it'll relax them, and it'll shorten the distance from that node to the other node.
Fair enough. Yeah, I have seen another thing.
In every step, it finds a new shortest path to one of the nodes in the graph. With every iteration, we find one of the paths to a new node, which is the shortest path to that.
Okay, these are all good, fine statements to describe it, right? I'm going to use this particular terminology. CXY is the direct link cost from X to Y. So DCDE is the cost of this link. Okay? D source where these variables are being maintained to node B. It's the current least cost estimate. Okay? So in the beginning, when node A wakes up, it knows dA equals 0. The least cost of itself is 0. That's just hard coded, right? It doesn't know anything else except that. dB it thinks is infinity, dC it thinks is infinity, dD, oh, this is d at dE, dG. All of the others are infinity. Just bootstrap. Okay? But over time, some of those will come, all of those will become finite if the graph's connected, of course. PV is the predecessor node along path from source to B. Over the course of time, Dijkstra's algorithm is going to compute shortest paths from, let's say it's running at node A, A is going to compute shortest paths to all of the nodes. Okay? In that process, PV is a predecessor node. So let's say this is the least cost path from A to G. We don't know, without weights on the graph, we don't know this is the least cost path. But if all the weights are 1, the least cost path would be 1, 2, 3. The 3 is 3 hops to the least. Okay. So let's say this is the least cost path from A to G. E is the predecessor node in that case. Okay, node along the least cost path. We'll use this varying dynamically expanding set n prime to denote the set of nodes whose least cost is definitively known. So when A wakes up, it definitively knows the least cost only to itself. This set n prime includes A itself and nobody else. Okay? That's all the terminology we need. I think I have the animation set up to show you not the algorithm, but just the initial addition here first. So initially n prime is just a node U itself. So, well, I showed you in this graph it's A, but in the slide, the node that's running this algorithm is U, okay, not A. So initially the n prime, it knows the set of nodes to which it knows the least cost definitively is just itself. For all of the nodes, it's going to see if it's my immediate neighbor. How will it know it's immediate neighbor? Well, it's just going to flood a message in all of its outgoing links and wait for acknowledgements from its neighbors. And wherever it gets acknowledgements based on that, it knows that they are the immediate neighbors. Okay. So to its immediate neighbors, it is going to say, dB, my current estimate of my least cost, is not infinity. I know I can get to them at least from this directly. Okay? So I'm just going to change, just so it's not confusing, I'm going to change this A to U, just so it's consistent with the I might keep going back and forth between the different alphabets. So initially, U knows the least cost to itself. N prime is therefore just the set of itself. It knows the current estimate of the least cost to its immediate neighbors. However, the current estimate, this CUV, this distance, or this link cost, that may not be the least cost path. It is entirely possible that the least cost path from U to V is actually UCDV. Okay? If this link had a high enough weight, this wouldn't be the least cost path. It's just that U knows that the least cost distance from U to V is no greater than CUV, the cost of the link to V. Okay? That's what this initialization is saying. Cost to myself is 0, n prime is just myself. I don't know the least cost paths even to my immediate neighbors yet. So what do we do next? How do we fill 9, 10, 11, 12, 13, 14? It's actually just 9, 10, 11, 12, 4 lines of code. Either code or like what do we say here with this terminology? What do we do here? Everyone else knows that as well. It's in the slides, of course, but I expect somebody to be able to recall it from memory and not just the slides. It is an iterative loop, so let me actually show you that as well. every step of the iteration, someone there, I think Anurag said, we're going to pull in a new node whose cost we now will whose least cost we definitively know. Initially that set is just you. You definitively know the least cost to yourself is 0, that's all you know. You know a bound on the cost to your immediate neighbors. It's no greater than the direct link. You don't definitively know the least cost unit. But in every iteration, until, what's the iteration? Until n prime encompasses all nodes, the entire set n in the network, the entire set of nodes, we are going to add in, pull in one more node to which we definitively know the least cost. That means its least cost will no longer decrease. We know for sure that that's the final least cost. Okay? So how do we do that? We find some node that's not already in the set of nodes to which we already know the least cost definitively. We find the node W such that dW, my current estimate of the least cost of that W, is a minimum. I pull in that node into n prime. Why? Because I can reason formally that this node's least cost will no longer decrease. It's now definitively known. Okay? Why is this? Let's look at this example. Let me also give some weights to this example. Okay? This is 23. Okay? This is 2. This is 1. This is 4. Okay? We don't right now care what the other link weights are. Initially, U only knows the least cost of itself is 0. It knows that the least cost of B is no greater than 23. DU or DB is 23. DC is 2. Right after initialization or bootstrap here. Every iteration, it's going to pull in at least one new node into this n prime, which initially consisted of itself. It is going to pull in that node, W, whose dW, current estimate of least cost of that W, is minimum. DE, DG, DH, DF, DD are all infinity right now. DU is 0, that's not going to change, that's already in n prime. DB is 23, DC is 2. So it's going to pull in that node whose D is the minimum, which is C. And now U is going to say n prime is equal to myself and C. So the claim is if you're pulling nodes like that, like on line 9, or line 9 and 10, the least cost to C will no longer decrease. You have found the least cost to C. It's very obvious from this picture why that's the case. It doesn't matter what these other weights are, okay? The least cost to C can no longer decrease below 2. It's very obvious. Why? Why is this? No matter what the path to get to C is, from U, it has to be either this way or this way. There's only 2 options for U, okay? In this example, in this step, it's very clear why pull now would be less than 2. If you go here, it's 2. If you go here, it's already greater than 2. Done. Okay, that's the proof in this example. But in general, at any step, this is going to be true. Okay? What do we do next? What do we do in line 12? You have all this all the terminology. So what is line 12? Fill in line 12 for me. Yeah.
You find DW for the neighbors of C. How more to know you recently for me?
You find D, let's say X, or X in neighbors of W, the one that pulled in, right? Okay. And then what? Like, what do we do to those DXs?
You assign it to CWX plus DW.
Good. This is it. That's all there is to Dijkstra. It's one of the oldest algorithms. In fact, the notion of algorithms didn't quite exist back when Dijkstra's algorithm, Dijkstra came up with an algorithm like this. Back then, computer science was a fledgling field, right? So back then, math was what, was the pinnacle of intellectual, mathematical sciences, if you will. The mathematician used to be content with determining the existence of something, didn't really care about how to efficiently compute something. Back then, it wasn't an important consideration, right? So algorithms, which are about efficiently computing something, this is one of the oldest, earliest instances, maybe the most famous of algorithms taught in computer science courses. This is all there is to it, okay? So, as GC said, we pulled in this new node C. We know definitively it's least cost. Now we're going to update our current estimate of the least cost to any other nodes in the network. The only ones that will be affected are the immediate neighbors of C. So we know the least cost of C is definitively 2. It's not less than 2. Therefore, the least cost of D can be no more than 2 plus 1, 3. And that's the only neighbor C has. Okay, so C is the W we pulled in here, and that's the operation we're doing. The new node we pulled in, which is the node that most recently got its least cost established for good. We look at its neighbors, all of its neighbors, and update our estimate of least cost. We bring down, in general, our estimate of least cost of its neighbors. Okay? So now we know n prime is u c in this picture, and we also know d well, it's a little unfortunate we know that this is 3. D of D is now become 3 with step 12 in this graph. Okay? That's still n prime. What is D of D? That still remains 23. D of D doesn't get updated. D of U is just 0, never changes. What's the next iteration going to do? Find the W that's not an n prime such that dW is a minimum. What's not an n prime? E is not an n prime. D is not an n prime. E, F, G, H, none of those are an n prime. But E, F, G, H, they're all still in infinities at this point. In the set that's not already in n prime, we have D, B, and these are all infinities. So the W that's going to be roped in next into n prime is going to be, this is iteration 1. Okay, this is iteration 2. It's going to be U, C, and D. Let's sanity check this claim again. The node we're pulling at this line, we know its least cost definitively. It will no longer decrease. So the claim is the least cost to D that was 3 that got pulled in here will no longer decrease. Okay? It's very obvious in this picture, no matter what the other weights are in this graph, the least cost to D will be 3, no less. Again, why is this? In this graph, it's very easy to argue. From you, there's only 2 options. You either go here or you go here. Okay? Here, it's a lost cause. If you go here, from C, there's only 1 option. If there were more than 1 option, those options would have gotten updated at this line. Okay, nothing happened at the time except that 1 option. Therefore, it's easy to see that no matter what the other weights are, the least cost to D is now definitively known, and it is equal to 3. So when we do the line 12 update at this point, to all of these neighbors, of which there is a few, well, 2 in this time. We will now know that D of D, now I need to give some weights here. I'm going to give this weight a 5, I'm going to give this weight a 3, let's say. Now we know that D of B is D of D, which is 3, plus 4, 7. It's no greater than 7, so I can update my 23 to 7. I also know at this point that D of the other neighbor, I'm executing line 12, other neighbor which is F is equal to 3 plus 3, or no greater than 6. Everyone with me? What is the next node I'm going to pull in to n prime such that its least cost is definitively known? Yeah? Yeah, we're just going to look at these three. 6, 3, and 7. D is already pulled in. These are the only two options. Therefore it's F. Right? That's it. That's all there is to Dijkstra's algorithm. Every step of the iteration, until all nodes are covered, you pull in a node such that your current estimate of the least cost of that node is the minimum. Having pulled in, you update your current estimate of the least cost of all of that pulled in node's neighbors. You're doing this until all nodes are pulled in, you know? Alright, so the slides have examples of a graph like this. Just walking through this, make sure you go back. If you've forgotten Dijkstra and this example wasn't quite clear, or you couldn't see because you're sitting at the end, the textbook has more than one example of this, so just skip over. But this is all there is to Dijkstra, right? Okay, I'm just going to quickly skip over this. What do you have at the end of Dijkstra? At the end of Dijkstra, you have a forwarding table. Why are we doing all this? We do the control plane stuff, routing algorithm stuff, in order to feed into entries into the forwarding table. The forwarding table looks like that, or look at this graph. Now let's look at that graph. Okay. From U's perspective, a forwarding table has a destination and outgoing interface. To get to V, the outgoing interface is UV. To get to X, the outgoing interface is UX. To get to W, however, the outgoing interface is not UW, even though you have a direct link. Instead, it's UX. Okay, because UXYW is a path of cost 3 that's shorter than the direct link to W. This can happen. Happens all the time in networks, right? What's the corresponding tree, shortest path? At the end of running Dijkstra's algorithm from a single source, it has computed shortest paths to all nodes. Those shortest paths form a tree. Okay, and that's the tree that's shown here. That tree, what's a tree? A tree is a graph. Complete the sentence. A tree, yeah? Joe? Yeah, tree is just an acyclic graph. Right? Notice that this has no cycles. So we remove some edges that were unwanted that also happen to remove cycles. We're left with a tree. That's the forwarding tree. And the predecessor to Z, the PZ is Y, PW is Y, PY is X, PV is U. These were being computed in the course of updating Dijkstra, okay, in the course of running the Dijkstra algorithm. But at the end, that's what we're left with. Okay. That's just another example that I'm going to skip over. It's all just rehashing stuff we looked at before. Complexity. What's Dijkstra's complexity? Well, when we say complexity, what are we talking about? Complexity can have different meanings. Are you talking about running time complexity, space complexity, you're talking about distributed message complexity. How much time and how many messages are being sent per event, what is an event, right, and so on. So it's a nuanced question what complexity means here. But if you just focus on computational complexity of running Dijkstra's algorithm, the algorithm whose pseudocode I just showed you, then it is working in n iterations. In n iterations, n prime will have encompassed the entire graph, all the nodes in the graph. Okay, so n is the number of nodes in the graph. It's working in n iterations, and you could say its complexity is order n squared, or big O n squared, which means it's asymptotically grows no greater than n squared. But in practice, n log n implementations are straightforward. So somebody out there, what was your name? The one with the hat? Yeah. Remind me your name again?
Ben.
Ben, right. So Ben said the first thing he said, I think, was you start out with a queue. And a queue will give you the n log n implementation, right? That's what helps you. How do you say, sorry, pick the node W such that DW is a minimum. You keep a queue, expecting in logarithmic time, you can update this queue, keep updating the minimum. Otherwise, you take linear time, which is the difference between log n squared. Okay. Message complexity. Every time something in this graph changes, let's say the link EG breaks, right? A squirrel can be cheated out. So E is no longer able to directly ping G. The move E is going to periodically keep pinging G to know if this link is alive, what its weight should be. If it finds now that the link EG is broken, it will set CEG, the cost of EG, to infinity, and send this LSA, link state advertisement. That's why it's called link state. It will broadcast this link state advertisement saying, hey guys, CEG is now infinity. It used to be a finite value, let's say 54, but now it's become infinity, thanks to Squirrel, and it's going to broadcast to it. That link state advertisement broadcast is why it's called a link state routing protocol. And that broadcast will go to all nodes, and therefore, that broadcast step is what fundamentally induces the message complexity in link state protocols. What is the message complexity of a broadcast in a network of n nodes and E edges? Did it say that already? Say reach out as message crosses order n links. Overall message complexity, order n squared. Okay, so let's ask this question of how many messages can broadcast induce? If some message starting with node, G may also discover this link's cost exchange, they may both simultaneously discover, simultaneously broadcast. But let's just focus on one node for now. Let's say E discovers it first. E has to send CEG equals infinity, this message to everybody in the network. What's the complexity of it? What is it at least at a minimum? Not big O. Big O is bounding asymptotic complexity. Okay. In order for CEG, this information, to reach all the nodes in the network, at least one message must reach every node in the network. Therefore, at least n messages must be sent in the network. So at least n. Is it just n, or is it more than n? So what exactly is it? So at least n messages are needed for a broadcast. What's an upper bound on the number of messages needed for a broadcast? Have you seen questions like this in your data structure or algorithms course? I assume you must have. But I'm not getting positive. Yeah, sure.
N squared.
N squared, sure, n squared is certainly a bound. Okay. Why is, but I'd say it's somewhat, it's a slightly loose bound. Okay, let's try to get another tighter bound. We know that a message is to reach every node, so at least n messages must be sent. If a message is sent over every single link or edge in this network, that ought to be enough too. If a message is going over every single edge in the network, it automatically gets to every single node at least. Okay? So we can say that the number of the messages needed for broadcast is at least n. It need be no greater than e, the number of edges in the network. Okay, so n plus e asymptotically is a pretty tight bound. Order n plus e, or theta n plus e. It's a pretty tight asymptotic bound on the complexity needed for broadcast. What's theta as opposed to big O? What's the difference between order n versus theta? Anyone other than Joe? Is being contributed, please see.
Theta means you grow at exact same rate as.
No
C.
faster or no slower. When you say order n, people often use order n as if it's theta n, but order n is bounding from above the asymptotic complexity. That means the function grows no faster than a linear function. Theta n is saying it grows no faster and no slower. So it is asymptotic equivalent. Right? So this is a pretty good bound on the message complexity needed. In general, the number of edges in the graph may be quadratic in the number of nodes in the graph. Okay, in general, the number of edges may be quadratic because the number of pairs of nodes is quadratic. So E itself may be on the order of n squared. And that's why a broadcast n squared is certainly an upper bound on the broadcast complexity. But as long as you have an algorithm that traverses every edge, that is good enough. And that's how broadcast algorithms are implemented in networks. Each node wakes up, on all of its outgoing edges, it sends the message it needs. That node further sends the message, relays the message on all of its outgoing edges. And as long as all edges are covered in about that much time, n plus e, the message is reached it. That's what flooding is. Okay? You flood in link state routing, you flood a link state advertisement, an LSA, on all of your outgoing interfaces until it reaches all the nodes. At which point they have an updated, every node has an updated graph, simply reruns Dijkstra, that simple algorithm which is Joe.
How often does it do this calculation?
This depends on the protocol. We'll look at OSPF in a little more detail. Either end of this class or beginning of next. Okay, so that's I think all I have to say about link state. Oh well, one more thing. Link state routing, like Dijkstra's algorithm, is dynamic, which means when an update happens, let's say the broadcast in the network graph is updated every node, runs recomputes short paths. But it's not load dependent. The weights of these links don't depend on how much traffic is on the link. One way to think about the weights of these links is just distance. These were roads and these were cities. Nodes were cities and links were roads. You could think of them as the kilometers or miles of distance, the edge weights. That's one way to think about it. Shortest path is literally the shortest path between 2 points. However, we all know in practice that if there's a lot of traffic congestion on the roads, the distance is not everything that we care about. We also care about the current traffic on those links, on those road segments. So what if we said these edge weights are load dependent? So back in the days, in the 70s, 80s, they tried load dependent algorithms and finally gave up because they're too complicated to work well. Why is this? Because if you make routing algorithms load dependent, they can result, that design can result in oscillations. So intuitively, oscillations mean that everyone sees, oh, okay, I-90 is extremely crowded, so I'm going to take I-84. So a large swath of traffic starts moving over from I-90 to I-84, and then suddenly they find I-90 almost empty, at which point they all figure out that, oh, okay, that's a better route, they move the entire traffic over there. In real world road networks, this doesn't happen because information is, Google's telling us constantly that which road segment is better to take. But in these kinds of secure networks, oscillations can happen for the following reason. Here's a very simple toy example to show you why oscillations can happen with load-dependent edge weights, not fixed edge weights like this. Okay? So in this graph, there's only one node C that has any traffic the same. I'm sorry, there's three nodes. There's only one destination A to which they're all sending traffic. C has traffic E bits per second, let's say percent. D has 1 unit of traffic. Sorry, B has 1 unit of traffic, and D has 1 unit of traffic. They're all destined to node A. Okay. And let's assume E is just a small quantity, like epsilon. Okay. Something close to 0, just a small quantity. So initially, node C is going to look at its options. It can go this way or it can go this way. Let's say it breaks the tie evenly, just goes right for the first time. These guys are just going to go along the direct route that they have. And let's assume that load dependent routing here means the edge weight is the load. The higher the load, the higher the edge weight. If there's no load, 0 is the edge weight. Okay? So on this link, there's E units of traffic from C. On this link, there is the E units of traffic from C as well as the 1 unit of traffic from D. So it's this edge weight becomes 1 plus E. This is E. And this edge weight is 1 because it's 1 unit of traffic. All the other edge weights are 0. We'll also make a simplifying assumption just for pedagogical purposes here that the links are directional. It's easy to expand this into a non-directed graph. Okay, so this edge is different from this edge. Okay, it keeps the example simple. But it can happen in a direct, not undirected graph as well. Alright. So now we're ready to see why oscillations can happen. If the state of the current traffic is like this, E is going to look at the fact that it is sending traffic along a route of cost 1 plus E. Whereas if it sent it left, the cost would simply be 0 plus 1, 1. 1 is less than 1 plus E, so E is going to switch from right to left. B is going to look at the fact that it is sending at 1 plus E cost here. But if it's sent along this route, it will be 0 plus 0 plus 1, okay, because these links are directed. 0 plus 0 plus 0 is 1, 1 is less than 1 plus E, so B is also going to want to switch. This is the current state of the network. So at that point, they will all want to switch leftward, and the new costs are going to look like this. At this point, all three are going to say, all right, right is better, and they're all going to switch rightward, and it's going to look like this, and this oscillation will keep on going forever. That's the oscillation problem with load-dependent routing. Now, in this simple example, you might say, well, why is E trying to switch from 1 plus E to 1? That's such a small difference with E small. And it knows it has its own E of traffic, and it knows if it switches, this will also increase to 1 plus E. Well, in general, there may be more than one node like this, and it's not easy for any node in a distributed, decentralized environment to know what the effect of other nodes will be. Okay. So if you go with strictly load-dependent routing policies, which they tried, couldn't get the network algorithm converted, would keep oscillating. An oscillation of flux, this is bad in networks. They become much harder to manage. It's much harder to debug or diagnose the problems. We want networks to work stably, right? Routes keep changing. One thing it's going to affect is TCP's reordering. Okay, triple duplicate acknowledgements will be treated as a loss. TCP will back up. Life will stop for everyone. Founders will win, right? So just flux is bad in networks. They become harder to manage. We want networks to converge to stable routes and be sending along the stable routes for long periods of time. So we don't do load dependent routing anymore. But it's not like routing is not aware of current load at all. It is. We engineer traffic and routing algorithms to take load into account. That's a concept called traffic engineering, which we'll see right after we have seen the three conceptual routing algorithms. We don't do this style of weight on the link is literally dependent on the load on the link style of routing. Okay, distance vector. All right, before I go to distance vector, questions on link state. Right. Distance vector routing algorithm is based on this very simple equation called the Bellman-Ford equation. It's an example of a dynamic programming algorithm. Okay. It's actually very simple. It's actually simpler conceptually as well as to implement it than even Dijkstra's algorithm. But operationally, to understand what's happening in distance vector gets much hairier because of the decentralized nature of the view. You don't have the global centralized view. You have this view in distance vector algorithms. Okay, so what's the Bellman-Ford equation? The Bellman-Ford equation is very intuitive and simple to understand, right? It says that the least cost dxy, the cost of the least cost path from x to y, that's what dx1 means, must be the minimum over all neighbors b of x of the direct edge cost from x to that neighbor plus the least cost from that neighbor that destination y in question. So this is saying, in this graph for example, let's move here, this is saying, the least cost distance from u to any node y, okay, let me add a y to this graph here. The least cost from u to any node y in this graph is the minimum over all of the neighbors of u, which is b and c, of the cost to go to that neighbor, plus the least cost from that neighbor to y. Okay, this is very intuitive, this equation, because the only possible ways to go from u to any destination y is to go through one of its neighbors. And to compute the minimum over all neighbors to go to that neighbor and that neighbor's least cost to that destination, we're done. We have our least cost to that destination. That's all this is saying. It is this principle on which distance vector algorithms are based, and the idea is to take this principle and turn it into an operation that looks very similar to this equation and keep doing that operation over and over. That's all there is to distance vector. So let's look at how it will work, right? Let's first verify with some more examples the Bellman-Ford equation as well. So this is a more complicated or fuller example, right? In this graph, it's saying the distance from V to Z is 5. For DBZ, here DBZ is the least cost distance from node V to Z. Why is it 5? It's 5 because this is 3. Oh, sorry. This is 3 plus 5, that's 8. 3, 1, 2, that's 6. So it must be the 2 plus 1 plus 2. This is 5. Okay. So we can see the least cost is V to Z is 5. Let's verify that Bellman-Ford equation holds for this node. dxz is similarly 3. dwz is similarly 3. You can verify this. and you can check that well, these three nodes are the immediate neighbors of some U. So you can check that the least cost distance from U to Z is the minimum over its three neighbors, Dx and W, of the edge cost plus the shortest cost distance. That's equal to 4. Therefore, duz must be equal to 4. And we can indeed see that 4 is the least cost of the duz. That's just another example. So this is very intuitive. It's trivial to prove almost. Bellman-Ford uses this idea in the form of an operation instead of an equation. What I showed you was an equation. Bellman-Ford is going to turn this into an operation that applies over and over until you get to the steady state where that equation holds. From time to time, nodes will exchange what are called as distance vectors. A distance vector is a vector with as many components as the number of nodes. The number of nodes in the network. Every node has a component. What does it mean? If I'm node 1, my first component is the least cost distance or estimate thereof to myself. So in my distance vector, the first component, if I'm node 1, will be 0 at bootstrap. My distance estimate to nodes 2 through n, I'm node 1, let's say, 2 through n, that is to all of you guys, let's say, is going to be infinity when I bootstrap. That's my entire distance vector. So there's a component for each node, and that component represents the current least cost estimate to that node. Okay. This is the equation we do. This is the operation we do every step. Every step when X receives a new distance vector estimate from any neighbor. I've not named the neighbor here, okay? Because it doesn't have a name that's in this equation. From any neighbor of X, when it gets a distance vector, X is going to update every component of its distance vector. And there's n such components in the vector as follows. It is going to update its least cost estimate to Y, component in the vector corresponding to Y, as the minimum over all of its neighbors of the edge cost to go to that neighbor, CXD, plus that neighbor's least cost to that node in question, Y, the dBY. This, remember, is an operation, it's not an equation, it's an assignment. In steady state, this will become an equality. That's what Bellman-Ford equation told you. This looks exactly like Bellman-Ford equation, but it's not an equation, it's an assignment. If you keep doing this over and over, you will eventually get to a point where it doesn't update anymore. The assignment is not going to update anymore. At that point, you will reach steady state. Okay? The operation looks identical to the equation except for the equality and assignment symbol difference. And that's all there is. This is the algorithm. This will converge to a point where these assignments no longer update the least cost distance. If over and over, I look at all of my neighbors and compute the minimum distance to any node in the graph as the minimum over my direct edge cost to a neighbor plus that neighbor's least cost distance to the destination in question. Everything keeps doing this over and over and over periodically. They'll find that the distances converge and these assignments don't update the values anymore. So like I said, this is all there is to the algorithm. The algorithm is simple to write down, the pseudocode to implement, but operationally it gets more complex, okay? So this part is easy to understand. You wait for a distance vector, recompute your estimates across all of your neighbors, you take the minimum direct edge cost plus that node's cost. If any of those change, you rebroadcast your updated distance vector to your neighbors. This is what we're doing iteratively. And we know that under most normal conditions, if they're not weird graphs like graphs with negative weights and so on, or negative or cycles with non-zero weights and so on, which is real world networks, it will converge eventually. It will converge eventually to a point where in this step, if AB to any destination is changed, notify neighbors, there's nothing to notify neighbors, nothing's changing. Which means that assignment operator doesn't change anything, which means you've arrived at development for equality, the steady state. Okay? I promise you that this is deceptively simple looking. It indeed is. Okay? So we have to look at it. We want to make sure we understand how this works. It can operationally be really clear. It is guaranteed to converge. Self-stopping is guaranteed to eventually converge, but it may take a long time to converge. Okay, so let's first look at an example of how it's okay. This is a graph. Okay. There's no significance to why it's rectangular like that, almost rectangular like that, but it is in the textbook. Okay. Most edges are one edge is not one, so it's a somewhat, asymmetry is the wrong word, but there is something going on there. Okay, it's not like a trivial hop-down base graph. At least one of the edges is not hop-down, and that will result in some interesting dynamics here. What's a distance vector? A distance vector is just a vector with one component for each node in the graph. In this graph, there's 8 nodes, so the distance is like 1, 2, 3, 4, 5, 6, so 9 nodes. Okay, 9 nodes in this graph. There's one component for each node. So the distance vector at A, the 9 component vector looks as follows. DAA. Node A's estimate of the least cost distance to itself is 0. At Bootstrap, this is what it has. Shortly after Bootstrap, it pings B and B, its immediate neighbors, and figures out that DAB is no greater than 8, DAB is no greater than 1. All the others are right now infinity. So shortly after Bootstrap, this is this situation. No, that's node A distance vector. Periodically, nodes are going to compute their distance vector, update their distance vectors as needed, send it to their neighbors, and recompute least cost estimates based on the received distance vectors using the Bellman-Ford assignment or Bellman-Ford equation like assignment operation we saw before. Okay. So this is an example. Nodes receive distance vectors from neighbors. So they're going to recompute this. They're going to send a new updated distance vector. That recompute part is the assignment operation we're doing, which was component wise for every component in the vector. Okay. So I'm going to just walk through a concrete example of how this update happens, which is okay. So initially, we saw that node B has that distance vector. Okay, this is the same as what you saw a couple of slides back. It says shortly after Bootstrap, it knows the least cost distance to itself is 0. It knows its immediate neighbors are finite. Everything else is infinite. That is node A's distance vector. All distance vectors have 9 components. Okay, that's node C's distance vector. All of them are shortly after Bootstrap. Distance to self is 0. So let's check that. Node C, distance to self is 0. Distance to B is 1. All the others are infinite. Okay. What's going to happen next? B receives distance vectors from A, C, and E. Okay. Those are the 3 neighbors. So that's E's distance vector. Similarly, E knows its cost is 0, and then it knows costs to B, D, F, and H are finite and equal to 1, and the rest is infinite. Okay. Now B is going to receive distance vectors from A, C, and E, its immediate neighbors. How is it going to update its distance vector and rebroadcast what to its neighbors? When B receives these 3 vectors from its 3 neighbors, B is going to do the recomputation. And notice that I made the graph deliberately now like this to capture this view, the decentralized view. Because this is all actually knows of the existence of other nodes, just like pictured here, but it doesn't know the topology, it doesn't know any edge weights to the rest of the nodes. It's going to get these three distance vectors, and it's going to recompute its distance vector as follows. For the first component, from D, so DBA, this least cost distance estimate from D to A. It's the value just before it got the distance vector from A was equal to 8. B thought DBA was 8. It would be after bootstrap. That's not going to change. A says DAA is 0, which is here. B is going to apply Bellman-Ford equation to say, what is my cost 8 of going to A and then going from A to A? That's just 0. But I'm already at cost 8. That doesn't change my estimate at all. So nothing useful or interesting happens in this step. Next step, DBC. Nothing useful or interesting happens there either. Going to C at a cost of 1, and then going from C to C at a cost of 0 is not going to change my least cost estimate to C. Things will become more interesting very, very shortly. Okay. What about the least cost to D? Where is D? Well, D is somewhere. We don't know where the topology D is because this is all the view D has. That's the decentralized view. However, D's cost, which was previously infinity, D didn't know how to get to D because it knew to get to itself was 0, this was 8, this was 1, this was 1, and then all the others were infinity. But now it knows that to get to D, it can go from B to A at a cost of 8, and then go from A to D. D is here, you don't see it. D doesn't know exactly where it is, but it knows that DAD is equal to 1. And so 8 plus the 1 that A is advertising, 9, is less than infinity, which B has for node D. And therefore, it is going to compute the minimum of 9 and infinity in nodes no greater than 9. What about E? E is saying it has a cost to go to D of 1. How do we know that? That's right here. DAD was right here. So B is going to say 1 plus 1, 2 is not only less than infinity, it's also less than 9. Therefore, its cost is updated to 2. Similarly, its cost, well, the E, nothing interesting is going to happen. To F, which is, I actually forgot where F was, but to F also it's getting updated from infinity to 2. G, it's not going to change. To H, it is going to change to a finite value. So why is this? Let's go back to the graph. In this graph, oops, that's our graph. D will know now a finite cost to D, a finite cost to F, a finite cost to H, but to G and I, it still has an infinite cost because it didn't get any useful information to get to G or I from any of these three immediate neighbors, A, C, and E. So that's why when you walk through those, to G and I, we still had infinities. In the next step, they will also become finite. Okay? See, tenseness in the class. So this is why I told you, operationally tracking what's happening with this inspector algorithm can get really hairy. This is hardly the end of why it gets hairy. This is also the reason why this inspector algorithm is not used in large networks. They're used in fairly small networks with hop count settings, not arbitrary edge weights. I'll tell you why that arbitrary edge weights can make it even more complicated. Okay. Our updated distance vector. So let's see what's left. This was the previous distance vector to B, shortly after bootstrap. After all of this, after one step of exchange from neighbors, this is the new distance vector, to which this is getting updated. So instead of cost to self is zero, cost to immediate neighbors is finite, just the edge cost, everything else is infinite. You've gone to cost to self is zero, cost to immediate neighbors has potentially decreased, and cost to some non-neighbors has gone from infinity to a finite value through those neighbors. And some of the costs to other nodes in the graph are still infinite. Okay? So that's the update, the recompute. If your distance vector changes as a result of getting distance vectors from your neighbors and doing some Bellman-Four-Style computation, B will re-announce this distance vector to its neighbors. Okay. So let's maybe look at one more example of what's happening at node C. So here still is bootstrap time. B is back to bootstrap time. This is not after the previous step. We're just looking at what happens at step 1, now it's C, before B has done its recompute. This is B's vector shortly after bootstrap. Look at it from C's perspective. What is Bellman for the iterative operation doing? It is looking at all the neighbors and looking at the least among the neighbors and going to that neighbor along the direct edge plus that neighbor whose cost distance to any node requested. From C's perspective, its distances to the other nodes in the network to B will not change because it's just going to remain 1. But as soon as B sends this over to C, C will know that DBA is 8, but DCA is infinity. So C will know that it can go at a cost of 9 to A. It will know that it can go at a cost of 2 to E. It will know that it can go at a cost of. That's it. That's all it will know after the operation. It will update its cost. This will become 9 from infinity. Cost to this will become 2 from infinity. This will remain at 1. It will not have any more finite knowledge of distances to these things. Okay, so that's the operation update it's doing. A becomes 9, B remains 1. E goes to 2. All the others are just going to be infinity. Okay, and I'm done with with everything that can happen with distance vector algorithms. There's other examples in text I'm going to skip over. Distance vector algorithms are propagating information through the network. Essentially, one hop at a time. So after the first iteration, information from C's vector will reach all the nodes within one hop of C, which is B. Initially, nodes A, D, E, F, G, H, I, they all think the distance of C is infinity. B doesn't think the distance of C is infinity. After one iteration, B will still continue to think the distance of C is finite. After 2 iterations, A, E will also think the distance to C is finite because they will get this information from B to go to C. After 3 iterations, these nodes will think that the distance to go to C is finite. Because when A tells D that it has a finite cost, D will get a finite cost to go to C as well, and so on. After 4 steps, which is the most amount of outcomes information can take to propagate, all nodes will have a finite cost to go to C, and all nodes will also have a least cost to go to C. So in general, in a graph, how much time it takes for the graph to converge to a point where the assignment operation doesn't change anything, which means the Bellman-Ford equality steady state has been arrived at, depends on the topology of the network. It depends to some extent on how far things can propagate. Okay? So, bad things I told you wasn't the last of it, the distance method. This is an example of a problem called a counter tree. This is easy to illustrate with just 3 nodes in the network. There's only 3 nodes here, X, Y, and Z. distance vector routing protocol is moving its travels quickly. So if this link cost changes from 4 to 1, that's good news. Some link has improved in its cost. Okay. Then very quickly, y is going to update its cost and say, oh, my direct cost earlier, my best cost was 4, because 4 was better than 1 plus 15. But now my best cost changes from 4 to 1, and then it's going to announce it to its neighbors. So in about 2 iterations, Z will know, in step 1, Y will update its cost to its as X of 1. In step 2, second iteration, Z will know that its least cost is 2, not 5. So good news propagates quickly. Everybody updates and they're done. But bad news propagates really slowly. So in this example, if the cost changes from 4 to 60, it will take 44 iterations for this network to be used. 44 iterations. This simple, puny, harmless looking triangular network will take 44 steps for all nodes X, Y, and Z to know the least cost distances. It's very important to understand why, with this, such a simple example, this can happen. Any guesses on why this can happen? You have all the ingredients to know why this can happen. When that goes, cost goes from 4 to 60. Just before that, Byx was equal to 4. Yeah, his cost from Y to X was, its estimate was 4. Every X was converged. When that goes to 60, Y is going to say, all right, my XY has become 60, but Z is announcing a cost of 1 plus 4, 5. Just before this event, BZX was equal to 5. Just before this event happened. Y is still getting this advertisement from Z. So it's going to say, all right, my direct edge has gone to 60. However, my neighbor Z is telling me it has a least cost distance to get to X of 5. And my cost to go to my neighbor Z is 1. Therefore, I'm going to update my cost to go to X as 1 plus whatever it's claiming. So I have a cost, least cost to go to X of 6. This might seem stupid, right? Because the reason Z is claiming it has a cost of 5 is through Y. But Y doesn't have that 5 anymore. But it takes Z's word to think that it does have a cost of 5, and it adds its direct edge cost to that to get 6. Why does this happen? In this example, you can clearly see this is the wrong choice. But in a bigger network, where you don't have visibility into what's happening in the rest of the network, you just take a neighbor's word. So this will become 6. Next step, Z is going to say, aha, I have a cost to go to Y of 1, and Y is telling me it has a cost of 6. So D, Z, X will get updated to 7. D, Y, X in the next step will get updated to 8, and so on, until they both realize that actually this 50 is the edge that they should be taking. That's what ends up taking 44 iterations. So in a protocol like RIP, routing information protocol, that's real world distribution. But the protocol, when nodes are exchanging distance vector every 30 seconds, it can take 30 seconds times 44 iterations if you use wait statements, right? We're getting restless here over time. So I'll end there. Project 2A is due very soon. I see a lot of Piazza chatter. I'm happy to take questions. You can look at your code for a few minutes. Yeah, keep the questions coming on Piazza. I see a few solutions that are passing all correctness tests. If by some chance you still haven't started, it's already high time to start. Okay? Unlike project 1A, in 2A, about 50% or so of the class passes all the correctness tests. So do not underestimate what is going to take. Do not underestimate the hardness of correct, simple